So what we've noticed is the KA24DE Nissan engine is having a resurgence of popularity. It's currently one of our most popular engines to build, and it's all happened in the last year. I don't know what's going on, but I think people are rediscovering this really good underrated motor. Back in the day, we used to get these and chuck them in the trash and put an SR20DT or a LS in there, but people are discovering that this is a really decent motor. With its bore-to-stroke ratio and everything, when it's turbocharged like this engine, it's a good torquey motor. It spools the turbo really quick, and it's responsive, and it's really fun. Now, we're building this engine turbocharged. I think this is a really good engine for a moderately turbocharged build. Like, I don't think this is the thing to make 1,000 horsepower. But, you know, if you keep it to 450 horsepower, she'll go all day. I mean, I think you can go 500 horsepower, but, you know, there's some developmental things. Like, there's the bore spacing's kind of prone to blow the gasket, and there's no really good, super good head gaskets on the market, so you'd have to O-ring and stuff like that. And that's all expense, and O-rings are a little bit risky. But, you know, keep it to 450, 500, she'll go all day. You know, due to the really long stroke, this engine doesn't like to rev, so keep the revs under 8,000. You know, we've seen some really weird block failures above 8,000, like the block will tend to crack in half, like right at the parting line of the main caps, believe it or not. And it's not really a lack of strength issue, but I think it's a harmonics issue from the long stroke. But it's something we've noticed, and you know, like if you have a street engine, you probably don't need to worry, but race engines, like revving to 9 grand, their life is somewhat limited, and the failure is usually catastrophic. So this isn't a super engine like a Honda K engine. You're not going to get 1,000 horsepower unless you spend some serious money. By that point, you might as well get a K engine. But you know, for a good, fun, moderate engine, I mean, I think Matt Powers was making, back in the day in FD, he was probably making like over 550 horsepower fairly reliably, but you know, that's being a little bit exotic. So I think a basic 450, 500 all day long. Just don't rev it. Keep your boost in the, don't exceed like maybe 25 PSI either, because then head seal becomes an issue. I would probably keep in the low 20s just to be safe. But here we go, cast iron block. We have ARP studs here. The ARP studs are great in an iron block. They're 180 PSI tensile strength, way stronger than stock. You can run more torque. You keep the keep that girdle nice and tight. You're not going to beat the registers out as easy. Pretty recommend for a turbo motor. This engine has oil squirters that keeps the underneath of the pistons cool and reduces the engine's likelihood to detonate, helps your cylinder wall lubrication. I think that's a good thing to have for a turbo motor. Come stock, leave it alone. Some guys like to block them off, but I say for a turbo motor, don't do that. We kind of cleaned up the casting on this motor. You know, like we kind of go over it with a cartridge roll lightly. Like we don't go crazy and polish it or anything, but we kind of knock the casting sand out a little, just do a little deburring. You know, it's not necessary to go crazy, and it's kind of time consuming, but you just kind of want to lightly go over it and get the entrapped sand out mostly. I don't think polishing it to help oil return is really a thing. That's just a lot of labor costs. I don't think it does anything. When you use studs, be sure to check your main bores to see if you need a line boring. Anytime you increase the tightening torque, it tweaks everything more. This engine had to be a line bored with the studs, so you could see it was a line bored. Not every engine's going to need it, but I'd say with studs, there's a good chance you're going to need to be a line bored. We use studs on the top. When you use studs on the top, you know, it's a good thing to maybe use a torque plate, because the same reason, you're going to more torque, you're going to have more distortion. I think these engines maybe need a torque plate a little more, because you know, some of your newer motors, the threads are way deep in the block, so you know, your distortion around the top's not going to be so bad. But these older engines have shorter studs. The threads are kind of more up here, and I think they tend to distort the bore more. So, you know, if you're running a studs and, you know, the iron block's stiffer than aluminum, but studs with the threads up here, more likely to need a torque plate. So, you know, that's another thing. You know, we put a really smooth surface finish on our decks, so you can run the MLS gasket. Since we run really low tension, narrow rings, we put a really fine finish on the cylinder wall, and we also plateau hone. When you look here, it's a pretty lustrous finish, and we do kind of a slightly coarser hone than we used to, and we plateau over it. That's because Lake Speed has done a lot of research. And if you pay attention to his videos on YouTube, that guy is Mr. Cylinder Seal. He knows everything. So we're kind of doing things according to what he says now. So that's why you see some little bit of a deeper crosshatch, like under the sheen of the plateau honing. You know, like building a turbo engine, I prefer to cryogenically treat and WPC the block. You should always cryo treat before you do anything. That's your first process before any of your machining or anything like that. And then WPC last. Our customer here didn't opt to do it. He did it for some of the internal parts, but not for the block. If it was my personal engine, I would do it. But overall, you know, I think this is a good, solid motor. I mean, I'm kind of partial to iron motors sometimes. I think iron's a really good block material. Little fun fact, back in the F1 days, when Honda was doing their winning motor that I think Senna and Alain Prost drove, I think it was the 1500cc turbo era, Honda actually chose cast iron over aluminum or any exotic aluminum type alloy. You know, it's an F1 car. They'd probably get the most crazy alloy if they thought it was better, but they chose cast iron for its stiffness and stiffness to weight ratio. So that's an interesting thing. Let's get on to the rest of the engine. Now we're talking about how the Ka24 has a really stiff, strong iron block. Part of that is due to this bottom end girdle. So this is a one-piece unit that keeps all of the main caps all integrated into one part, and that really helps the bottom end stiffness of the motor. One weak point of the Ka24 motor, though, is it doesn't like to rev. Now, when we used to race in SCCA GT3 and in stadium trucks and stuff like that, we would rev the crap out of these motors to like 9 grand and stuff, and when you rev much above 8, the block breaks in half, like right about where the parting line of this girdle is. I mean, the block would literally break in half, and it's some kind of harmonic that's going on within the motor that does it. Now the motor is strong, but it's susceptible to harmonics and vibration above 8 grand. And one of my theories is that the Ka24 has like a half counterweighted crank. You see like a lot of other engines like Honda K motors or the SR20, it has a full counterweight crank, so every throw has a counterweight. And I think this helps balance the crank better and have less torsional things going on at high RPM. I mean, I noticed that most real performance motors have full counterweights for the most part, and this is like half counterweight. It's probably because Nissan never intended for this engine to rev that high. One thing I can say though is that this crank is a really good crank. It's really strong. I've never seen one of these cranks fail. The block will probably fail before the crank. It's a really good unit, and you probably don't need to replace it, because I really don't recommend that you try to go you know, above 8 grand. You go above 8 grand, you have to get a full counterweight Sonny Bryant crank or something, and that's mega bucks. Keep below 8, run the stock crank, you'll do pretty good. Now this crank, we balanced it We did some micro polishing of the journals, and then we WPC'd the crank. Kind of see the milky, smooth texture on the journals. The WPC makes everything smooth with less friction. It also gives that compressed skin where that cracks have a harder time to propagate in, so it increases your fatigue strength. If this was my engine, I'd probably cryogenically treat the crank too. I'd probably cryogenically treat about everything in the engine. CTP Cryogenics does all of our cryo. I think cryo is a pretty darn good thing. It's not all like smoke and mirrors. Like, it really does metallurgical changes in the metal. It refines the grain structure. It stress relieves everything, and it converts more of the austenite to martensite, which is a stronger crystal matrix of like a ferrous metal. So it has a lot of advantages. Our customer didn't opt for cryo. I would have done cryo, then WPC. When you do that, you want to do the cryo first, then WPC. This motor has only been WPC'd. So now we got the block, the crank. Let's go on the rest of the bottom end. You've probably heard me in past videos, like I always caution about using studs and aluminum blocks unless you really need them. Like, let's say you're a big boost motor or you're going to an all-out motor. It's because the strong unyielding stud doesn't grow as much as the aluminum, so the aluminum expands more and you get distortion of bores in your your bearing bores and your bores for your piston. That's the reason why factories use torque to yield. So for milder motors, I just recommend going torque to yield, and those kind of motors, and studs only for a max effort. Well, the KA is a iron motor, so you don't need to worry about that. And for a turbo application, head seal's a little bit of a problem, so we used ARP studs. This is made out of their proprietary alloy. It's probably some variant of chromoly, probably with some more nickel in it. I don't know for sure, I'm just guessing. But they're 180,000 PSI strength, which is probably, like 60% stronger than stock. They have rolled threads, heat treated, good stuff. We use ARP studs, an iron block, and the mains and the cylinder head. When running ARP studs, you gotta be sure and use their assembly lube. This is critical for getting the correct torque. You also have to use their nuts and their hardened ground washers. That's critical for getting the proper torque. When you use ARP studs, a lot of people just throw them in the motor and away they go. But you're running a tighter torque, you get different distortion. So I really recommend that you use a torque plate on your top end with the ARP head studs. And when you do the bottom end studs, you align bore your motor, or at least check it to make sure you don't need align boring. Now these Ks are pretty beefy, and they almost never need align boring, but with studs, this one needed align boring, so it's critical, because it would suck to start throwing your motor together and you find that the crank doesn't spin or something, which happens. And a lot of guys will have a running engine in the car and they'll throw ARP studs on the engine in the car, and I always think that's a big no-no. A lot of guys get away with it, but sometimes really bad things can happen. So, that's the procedure. Put the studs in before you do your machining, and do your machining with the studs in place at their proper torque. Moving on the bottom end, we run, on this engine, we run Manley rods. Now I think Manley is a fantastic rod for the price. The material is like a 4340. That's a high nickel, high molybdenum steel. Think about it as chromoly, but even tougher. The nickel gives it a lot of toughness, a lot of impact strength, and resistance to cyclic fatigue. Manley has their own rod bolts, but as an extra price option, they have ARP 2000 bolt option. Now this is a pretty darn strong bolt. For all-out race engines, I like to run 625 CA, but for almost everything else, I like to run ARP 2000. So for me, when you get the manly rod, no matter what, the ARP 2000 bolt option is the way to go. I mean, it hardly costs anything more, and the rod bolts is one of the most highly stressed parts in the motor, so why try to save a few bucks there. Now, these rods have some features I like. Really nice quality. It's forged from a billet to near net shape, and then it's CNC machined to the final shape. You look at the workmanship, like you can't even see the parting line. I mean, that's some pretty tight main cap fits. I like the pin oilers. Like, it uses 2 holes, like at the bottom of the pin, kind of in the inside of the beam. What I like about that is that hardly weakens the small end of the rod, and the small end is pretty highly stressed, and it's small. A lot of rods have the oiling hole at the top. A lot of really good high quality rods with a great track record do this, and there's really nothing wrong with it, but I prefer 2 small ones down here where the stress isn't as high as at the top. So I think that's a good design feature. We also WPC treated the rod bolts and the rod itself for more fatigue strength, and also to get some more lubricity and the small end bushing. If it was my motor, I'd probably cryo treat it too, but customer opted to just WPC. I think that's still good insurance. So really good rods by Manley. Our pistons are from JE, and there's something about a lot of you guys that build KA24s. A lot of you guys, when you talk to us, you want us to build a strong motor so you can turbo it later, and that's not a good idea. Mostly for 2 reasons. I mean, the main difference between us building you a naturally aspirated one of these and the turbo one is the compression ratio on the pistons and the center line of your cams. Now, the center line of your cams you can adjust with timing gears, but your compression ratio is definitely different. So you look at this turbo motor, the dish is a lot deeper than this NA one. So this NA one, it's built for California gas, so the compression is 10-to-1. If you live in some other state and you can get 93, or you just have gas that doesn't suck as bad as ours, we can build 11.5-to-1. But California, our gas, especially our summer gas, is so bad, we have to be really conservative. So, this is a 10-to-1 piston. This is actually, this is a 10-to-1 piston. This is a 9-to-1 piston. So if you're driving around all day on 9-to-1 naturally aspirated, your engine would be kind of doggy and it would suck. Or if you tried the turbo, a 10-to-1 or 11-to-1 motor, if you're going to be running the E85, that's probably pretty cool. But on pump gas, you're going to be running real close to the detonation limit. And I always tell people that if you're building a street engine, who cares if you make 10 less horsepower? You got to be more conservative so your stuff will, never break. And don't run on the cutting edge. You're not racing for money. It's your fun car. And even if you're doing track days or drift days or things like that, you don't need to make every last horsepower. You're better off having the engine last longer. So anyway, build your turbo engine for boost and build your NA motor for being on the motor, but don't try to make your NA motor a boosted motor, unless you're going to be running some kind of better fuel. That's what I have to say on that subject. But we're running JE pistons. It's a really good piston. It's a shelf piston, but their JE's shelf piston is really packed with features. So this is their FSR forging. It's made out of 2618, so that's a low silicon alloy. It's ductile, it's tough, it can resist detonation. It's just the perfect piston for a turbo motor or for hard use. So I think that's the right choice. In the past, 2618 pistons have been kind of noisy, especially on startup. They kind of sound like a diesel. But JE has really advanced skirt designs, and the cam profile is really good. And you know, I've noticed that in the past 10 years, JE's really improved their skirt design, so their 2618 pistons really aren't that noisy, and I'm actually really impressed. And they also run a pretty tight piston to wall clearance. Normally 2618 expands a lot, so you have to run a really loose clearance. Back when I was a kid, you know, we'd run 7 or 8 thousandths of piston to wall clearance, and 2618 engines sound like diesel engines, especially when they're cold. But you know, lately with the advanced, you know, like thermal, I guess CAD, being able to do thermal analysis, and you know, with the skirt designs and precision machining, 2618 pistons really aren't that noisy anymore, and they can run pretty tight clearances from 3.5 to 5. So that's way tighter than back in the day when I was a youngster. So anyway, it's a great material. The FSR forging is to me, I really like them. The thrust side of the piston is wider, has more area, so you have more bore stability. Piston doesn't rock around, your rings seal better, and everything lasts longer. Engine's quieter. The non-thrust side is really thin and like a slipper skirt, so you have the lightweight and the low friction of having a narrow skirt. Wide where you have the load, narrow to make it light, and less friction. The FSR is a strut type forging, so you know, the pin boss is kind of narrower and lighter. And you have these flying buttresses going up into the pin boss to keep it strong. You have undercrown milling to get rid of excessive weight. Now this piston's been WPC treated, so it's kind of hard to see the milling marks, but you know, it's there. The piston also has a pressure equalization groove to help the second ring maintain a good seal. It's a really good piece. Like, I'm really impressed of, you know, how feature rich their piston is for a shelf piston. I have no problem rocking this in a race car. I think it's great. You know, for the moderate boost that the K24 can handle, it's a perfect design. I mean, if you're going to try to get 1,000 horsepower, you know, I'd probably design the piston a little different, but hey, the block really can't handle 1,000 horsepower, so, you know, why try? So I think that's a great piston. The piston pin is great for the application. It's a medium thickness wall steel pin. I really hate running those super light tapered wall tool steel pins because I had a lot of problems with the pin flexing and, you know, grabbing the bushing and causing things to break. So I don't try to save every gram of weight. So I like a straight wall, moderate piston pin for, like, you know, moderate boost and, you know, pretty hot NA motors. I don't like going too crazy. This is like the perfect pin for this kind of engine. The piston rings are pretty much state of the art. They're low tension, low friction. The number 1 ring is a steel ring. It's 1.1 millimeters, I think. Don't hold me to it exactly, but it's pretty thin. Steel. It has a nitrided finish. Nitriding is like a hard surface treatment. Converts the surface to iron nitride, which is like a ceramic, and it's really hard. It lasts forever. It's slippery. Number 2 ring, I think, is a 1.2 millimeter. It's also steel. It has a phosphate finish, and it has a Napier profile. Napier profile has a little hook on the face. What the hook does is it's low friction, high surface point loading, so it seals really good. Really narrow face, so it wears in, breaks in quick, and conforms to the bore quick. Really like Napier profile for number 2 rings, and It's kind of spreading throughout the industry. I think JE is one of the first companies to widely adopt it, but there's a reason it works really good. Even though it breaks in quick, it still lasts pretty long, so don't think that it's going to wear out right away, but it'll start sealing right away. The oil ring is narrow, low tension. Narrow is okay as long as you have enough drain back holes, and the piston has enough of that, so why have all the excessive tension? The last thing we want to talk about in the bottom end is bearings. We like to run King bearings a lot, but when King is back ordered or they don't make an application, we really like ACL also. Either bearing is a really good bearing. Your ACL bearing is a tri-metal bearing, so it has a hardened steel backing plate. Then it has a first layer of bearing material that's really hard. I think it has a lot of copper compared to lead, so it's like a harder material, so it has a good load bearing capacity. The next layer is a layer of bearing material that has more lead and less copper. It's softer, so it has better embeddability. So like if debris is in your oil, like it can embed into that material and not chew up your crank as bad. And the top layer is like a flash layer of zinc plating, which kind of really helps. Like when you start your engine, the oil pressure is low, or it's a brand new engine, the zinc acts like an anti-scuff layer until the oil pressure can come up. We WPC treat our uncoated bearings like this. In a lot of OEM testing, WPC treating the bearing improves the load bearing capacity by 15 or 20%. It's been proven by a couple of OEMs, so we'll take their word for it. And we haven't had a WPC treated bearing fail yet, knock on wood, but we think it's a pretty legit thing to do and really good bang for the buck. So that's the bottom end. So let's talk about what we're doing for the head. Now, a turbo engine, especially like one with moderate power, doesn't really need a lot of head work. We just kind of clean it up and make it nice. Now, for valves, we're running SuperTech valves, which is one of my favorite valves. It's a one-piece forging. It's not a spin-welded stem. To me, a one-piece forging is stronger. You don't have to worry about the weld failure. Now, there's a lot of really good valves made two-piece, but to me, the engineering person in me thinks one-piece is probably the way to go if you had the choice. Our exhaust valve is Inconel. In a turbo motor, your exhaust valve temperatures are really high, so I think it's really critical to run an Inconel valve. Inconel is kind of like one of those super alloys that can withstand a lot of temperature. It's an alloy of mostly nickel and copper. It takes 300 or 400 degrees, I think, more than what stainless can take. The exhaust valve itself has a kind of a tulip contour and a reduced stem. Now these features, for the exhaust gas flowing out of the chamber, the tulip kind of helps the flow make the turn to the exhaust port, so it helps the flow. And the reduced stem gives you more area to flow. And some people have tested that and seen a significant gain. I can't say it helps X amount because nobody's paid us enough to flow bench one of these heads, but it can't hurt. The intake valve is stainless. It's a one-piece forging. It's a nitrided coating. Like the rings, nitriding is that hard, lubricious layer that lasts a long time. On the intake side, it's been found that a flatter profile will help the flow go from the port into the combustion chamber better. It has the reduced stem, which also helps flow, and this flat contour helps the flow spread out into the combustion chamber. So the shapes are optimized for in and out. I can't say enough about SuperTech. I really like their products. The cylinder head, I feel like for a moderate power turbo motor, especially you're not pro racing and you don't need to get the maximum amount of power. I kind of feel like these engines are pretty happy up to about 450 and then head seal starts to become problematic. So if you keep it under 450, heck, just turn the boost up a pound or two more if you want a little bit more power, because headwork's expensive. So our port is like stock. We did a good Newen valve job. Newen is a CNC valve cutting machine that instead of having a cutter, it uses a tool that's spinning around, and it cuts a smooth contour from the combustion chamber to the 45-degree seat. Then it cuts the straight 45 seat, and then makes a smooth contour that extends about a 1/4 inch into the port. So it cleans up the area between the valve seat and the port wall, which is often a pretty bad mismatch. And you know, you gain a lot of power from that alone. I mean, on some engines we've seen 50 horsepower. On a 4-cylinder, it's somewhat less. I'd say that like between 10 and 8 horsepower is probably a reasonable guess. We run a 1 millimeter bigger SuperTech valve on both sides. The reason for that is we could, as valves wear, they tend to sink into the seat. And when they sink into the seat, that really negatively affects flow. And if we go a little bit bigger, on 1 millimeter, we can have the valve nice and high on the seat. And that really helps low lift flow. Since the valve's a little bit bigger, we unshroud the combustion chamber where it comes close to the valve. You know, we give it about 1 millimeter layback so you don't have shrouding caused by the big valve. And really for a turbo motor, that's all you need to do to the head. You know, these K24 heads actually flow really good. They flow about 18% more than an SR20 head, for instance. Port's design is nice. It's a low volume, high velocity, so it's not, you're not going to be laggy. It's going to come up on boost quick. The combustion chamber is a shallow included angle. It has quench pads. The quench pads are going to give, you know, squish the fuel air mixture toward the plug, get better ignition. The squishing action also gives turbulence in the chamber, so you get a more homogeneous mixture for better combustion. And you know, the shallow included angle has less of a surface to volume ratio. So your heat doesn't get retained in the chamber. Then the turbulence, you know, gives you a nice, compact, efficient chamber that doesn't detonate. Like this engine will resist detonation more than like an SR20 will. The SR20 has more of a pent roof design, and you know, it's just not as efficient, and it's more prone to detonate. So, you know, we don't do a whole lot for the head. The K head's pretty good. For a head gasket, there really isn't much performance gaskets on the market. You have a choice of like a Cometic or a Tomei head gasket. They're both 3-layer MLS gaskets. They don't have stopper layers, so they're not the greatest, but that's, you know, a good reason to use head studs for a turbo motor. I mean, they'll get the job done. You know, I'd prefer a stopper layer gasket, but no one makes one. There's also a copper gasket available, but I don't think copper gaskets reliably seal the coolant, especially on the street motor. A lot of guys disagree with me, but you know, like I've tried copper coating, all kinds of gasket cinch, Yama Bond, all kinds of stuff. But to me, a copper head gasket inevitably consumes like water. Like you have a good combustion seal, but it's one of those things when you pop your hood, you'll always smell some coolant, and your coolant will be getting consumed, it'll be going down. You have to keep an eye out on it. I mean, it's not going to be pouring water out of the side of the motor, but it's not really a great seal. So on the street motor, you know, if this was a race turbo motor, you know, maybe I'd try the copper, and you got to live with some of the drawbacks. But, you know, for the most part, I'd rather run an MLS gasket. People will probably flame me in the comments, but hey, that's my experience. For camshafts, on these motors, we only run Jim Wolf technology. Their cams have a big advantage over the others in the market, and I'll show you why. Jim Wolf technology cams are designed around the VQ follower. Now these VQ followers will fit right in the K24 head. They're lighter weight. They don't have a separate adjusting shim like the stock follower. It's all built in as one unit. So it's a lot lighter. It's probably 50% lighter, so you have less of a chance of getting valve float. These VQ followers have this little nub in there, and the nub is different heights, so you buy different thicknesses of these things to adjust your valve clearance. They're DLC coated for less friction and long life. They're a pretty cool unit, but the most important thing is, you know, the shim is the area that the cam has to rub on. So you can see it's a couple of millimeters smaller than this VQ part. You know, the wearing surface can go all the way out to the edge, and that 2 millimeters makes a big difference with how radical of a cam profile you can run. The other thing is when you rev really high in these, if you get any kind of float at all, like tag the limiter really hard or rev a little bit high on a downshift, this shim will shoot out like a tiddlywink, and you know, there goes everything. I mean, it's going to chew up your cam. Maybe you'll drop a valve, and there goes your whole engine. So you never have to worry about that with these. The difference in the cam profile is market. I mean, it's hard to tell by eyeballing it, but if you look at the JWT cam compared to, you know, other ones from other companies, the lobes are higher and they're steeper and fatter at the same time. So the JWT cam has probably about 40% more area under the curve. So for the same duration, the valve is open 40% longer, so you get more flow, more VE. You don't lose any bottom end, but you get a lot more torque, power, and your power band can extend. So JWT cams have the most area under the curve. The diameter of this really limits what a K24, you know, its maximum power and its maximum revs. Like you put a bigger cam, but you know, if it runs off of here, the cam will chew up and that'll be it. So this is the limitation, this diameter, of how crazy you can go with cams. JWTs take the biggest advantage of that whole thing. I don't think any other KA cam grinder in the market does that. They all design their cams around this. JWT makes adjustable timing gears. I don't think anybody else in the industry makes these for these motors. This is super critical. When you rebuild your engine, you surface your head, surface your block, align bore your block. All that distance shrinks up and your cams tend to get retarded. A lot of people don't bother to degree in their cams, but when we build an engine here, we degree in the cam and we make it like what the cam card says it's supposed to be. And it's usually off. I mean, off 4 to even 8 degrees sometimes. And, you know, most people just send the engine out the door, but I think that's one of the reasons why a lot of the engines that other people build are soggy, because that's a detail that gets skipped. The other thing is, being a turbo motor, if a customer wants a turbo motor, we'll probably spread the lobe centers and run them on the 112, 114 degree center line, and you know, naturally aspirated will probably run at 108, 110 or something, and that makes a big difference between you know, torque. And then on the turbo motor, it helps prevent you from blowing boost out the exhaust port, and that's probably one of the biggest differences between a turbo build and a non-turbo build. When you run JWT cams, you should always run their valve springs. The harmonics of the JWT valve spring is designed around the acceleration profile of the cam lobe. So the JWT lets you run a lower tension spring and still not get valve float. Lower tension means less horsepower loss in the valve train, longer life, less friction, more power. So JWT cams run JWT springs only. Don't use some other company's dual valve spring or something. You'll lose power and you probably won't pick up any additional RPM capability. That about sums it up for our Turbo KA24DE engine build. You know, we can build the single cams. Most of the stuff is kind of the same. Like I said, keep your horsepower reasonable. Like 450, it'll go all day. This is actually one of our favorite motors, and it's super underrated, and don't throw yours away. They're getting rare and hard to find. So if you like this content, be sure to subscribe to our channel. Go to MotoIQ.com, go to our web store, buy some stuff. It helps fund our stuff. And I'm sure there's days of reading for you at MotoIQ.com. A lot of tech out there. So hope to see you again. I hope you enjoyed this video.